Hi everyone, this is our project called Prologix. Next slide. These are our teammates with whom collaboratively we did this project. Today in this presentation call, we'll be going over introduction, grammar design, features, design flow, sample code run, and future scope. Coming to the introduction, Prologix is basically a logic-oriented language designed with inspiration with traditional languages like Python. Our goal was to create a language that feels familiar to developers but still allows for expressive logic-based constructs. The language supports core features such as loops, conditionals, and arithmetic operations, making it both powerful and intuitive. We built this language using Antler 4 to handle lexical and syntax analysis, enabling a structured compilation process from tokenization, parse tree generation, and final interpretation. We chose Python for the interpreter due to its flexibility and performance, and currently Prologix is optimized for the Windows platform. Overall, Prologix provides a strong foundation for logic-driven programming while being easy to learn and use. Now I hand it over to Deeman.
Yeah, thanks for that, Pawan. Now that we have heard about the inspiration behind Prologix and how it draws from Python simplicity, I'll walk you through how we structure the grammar, define its rules, and develop the core features that make Prologix both expressive and initiative. Next slide. Yeah, we begin with the grammar design, which is the foundation of the language. The first thing we did was define the core literal types. Int literal for integers, dec literal for decimals, string literals, and Boolean literals. These ensure the language can interpret and work with different data formats during execution. We then added strong support for control flow constructs, including if, else, switch case, and ternary expressions, which enable expressive and flexible logic structures. All major arithmetic and logical operators like addition, subtraction, multiplication, division, and or are supported. For iteration, we support while, do while, and for loops. This grammar was implemented using Antler 4 and saved in a .g4 grammar file. The grammar is modular, splitting simple operations like assignments and print statements from more complex structures like branching and looping. This separation improves readability, extensibility, and parsing efficiency. Next slide. All of our grammar rules are defined in the grammar blueprint.g4 file. This file is used by Antler to generate both the lexer and parser, which work together to break down code into tokens and build a parse tree for evaluation. The entry point is the program rule, which accepts either a list of statements or function definitions. Statements are divided into primitive statements like variable initialization, value assignment, function calls, print operators using display and return statements, and complex statements handled via flow decision or loop construct. The flow decision rule combines if-else statement for if, else if, and else, scenario options for switch case logic, and ternary statement for compact conditionals. In scenario option, we support multiple case options and an option default option, which offers flexible multi-branch control. These support different value types like literals and identifiers. This structure ensures Prologix handles a wide range of logic patterns while staying readable and clear. Next slide. This slide features on loop expressions and functions. Prologix supports while loop for precondition loops, do while loop for post-condition execution, and for loops with an initializer, condition, and updater, just like the traditional languages. The expression rule supports arithmetic logic, relational and logical operations, and ternary conditions of the form condition, true value, and false value. We use relation and basic expression rules to manage comparisons and nesting. Functions are defined using the func rule, which includes a name, parameter list, return type, and a block of statements. We also include init statement for declaring type variable func call for involving user-defined functions, log using the display keyword, and return back statement to return values. This gives Prologix strong procedural capabilities and modular design. Next slide. This slide defines all keywords and literals. We define literal types like int literal, decimal literal, string literal, and Boolean literals. Logical operators like and or no, and or. Uh, Type specifiers like integer, string, Boolean, decimal. And we also use expressive keyword based relational operators like equal to, greater than, less than, or equal to, and so others. This makes Prologix syntax both readable and beginner friendly, especially for people coming from a natural language or logical background. Next slide. This final grammar slide includes symbols and formatting rules. Tokens like colon, equals, and comma provide structure to statements. Arithmetic symbols are defined via incremental and decremental operator for multiplication and addition and subtraction, multiplying operator for multiplication and division. Identifiers are ANDed using the token name rule, which accepts alphabetic tokens. White spaces and comments are managed using empty space to skip the spaces, tabs, and line break. Prologix comment to ignore line starting with a percentage symbol and percentage symbol. These rules help maintaining clear parsing and prevent unnecessary noise in the interpreter. To wrap things up, here's a summary of Prologix key features, all enabled by the grammar we just saw. Next slide. Prologix supports control structures like if, else, and switch case, giving developers full control over logic branching. It includes three types of loops, while, do while, and for to handle all the iterative requirements. The print statement uses the display keyword, making the output straightforward and easy to understand. Prologix includes support for all standard arithmetic and logical operations like addition, subtraction, multiplication, division, and or. It features a range of relational operators using keywords such as equal to, greater than, less than, equal to, etc. The language supports type literals including integers, decimals, strings, and booleans, which are passed using specific token rules. And finally, it includes support for ternary expressions, which allow concise one-line conditionals using condition, true value, and false value. All these features combine to make Prologix a logic-first, expressive, and human-readable programming language. Now I hand it over to Rachna to continue.
Thank you, Dhiman. In this section, I'll walk you through the design flow that represents the journey of a Prologix program, starting from a simple source file as an input all the way to producing the final output, capturing the complete life cycle of execution, from parsing and analyzing the code to interpreting and executing it. Let me walk you through each step in this flow to show how our interpreter processes Prologix code. The process begins with the end user passing the source file by giving the file's relative path as an input to parser driver file. It further reads the source file using Python's file handling, which loads the entire source code as a string for processing. This string output is then fed into the components generated by Antler. Using our grammar, Antler generates two essential components, namely lexar and parser. The string output, which was generated in the previous step, is fed as an input to the lexar. Lexar then scans the input, breaks it into the stream of tokens, such as keywords, variable names, literals, and symbols. The next step is parser, which takes the stream of tokens and builds a parse tree based on the grammatical structure we designed. This parse tree represents the hierarchical meaning of the code. After the parse tree is generated from the source code, our custom-built interpreter takes over. Our custom interpreter is built by extending the grammar blueprint visitor class generated by Antler. The interpreter uses visitor pattern, evaluating each node according to the semantics we have implemented, such as variable assignments, control structures, or function calls, and ultimately produces the final output of the Prologix program. The entire interpreter is invoked from the main function that takes user code as input, parses it, and passes the parse tree to the interpreter for execution. The output, what is yielded by our custom built interpreter, is what you see as the result, which is the actual execution result of the user's source code. Now I'll hand it over to Rachit.
So I'll be going through the sample codes and how we run it on our project. So these are some of the sample codes that I've displayed on the slide. So I'll be switching over to our VS Code to show you the complete process. The only thing we should note is every input source file that we have should be stored with the .prologix extension. So coming to VS Code, this is our folder structure for our project. You have your data files. Then you have the dependency for the Antler jar to run. Then we have our documentation file and our source file in which our generated files are there, which Rachna explained that we, generated the lexer and the parser file. And then we have our interpreter and the token generator file in our runtime folder. So I'll be taking some sample examples to show you how we run our code. So if we look at, let's say we look at Boolean. So in our grammar, it's defined, uh, we have a token literal called Boolean, which was explained by Dhimant. So we can set it to true, false. All of this is defined in our grammar. And the result variable here is doing A either B, which represents A or B by our grammar. And display is used to print the statement, which is the result. Similarly, if you look at not operator, it is a unary operator, but then it is, combining A and B and then doing a negation of it. So to run this, what we have to do is we have to give the file path. So let's say this is our file that we want to run. So right now it says arithmetic, but I'm going to show you how to run the Boolean input. So if you look at it, A is true, B is false, and C is true. So A and B is supposed to be false. And if you evaluate the rest of it, it's all going to give you true. Like Rachna explained, the whole process is based on the parse tree generation and our interpreter, which is the evaluator, passing through the tree to get us the output. So if you see, if we run our interpreter, if we run our interpreter logic to generate the parse tree, this is how it shows. I'll show you running that. We have also enabled the GUI option to make it more clearer for everyone to understand. So if you want to actually just see the output and the parse tree on your terminal, all you have to do is give parse tree equal to true, and this prints out the parse tree for you, and it gives you the output as well. But since this is very difficult for us to read and understand clearly, we have also given you a GUI option. So we give you GUI equal to true, and this opens a pop-up window where you can expand it and see how the parse tree is generated. So you can go on expanding it. You see that our code, every line is becoming part of our parse tree, and it's mapped as per our grammar. So it's nested, like basically what is shown here is in a GUI format. And once you close this, you still get your result printed. And that's your GUI tree and the output. And now Pawan will take over.
Yeah. Coming to the future scope of the project, there are several directions at which we want to enhance Prologix. Firstly, we want to add support for advanced data structures like arrays, lists, and maps to improve data handling capabilities. We also plan to implement structured error handling to try and catch blocks, which will provide better diagnostics and safer program execution. Finally, to broaden accessibility, we are working towards making Prologix cross-platform so that it can run smoothly on Mac OS and Linux platforms as well. These upgrades will help Prologix grow into a fully featured, developer-friendly and programming language. I guess that's the end of our PPT. Thank you.
Thank you.
Thank you.